Welcome back. In this module of statistical methods for bioinformatics, we discuss statistical testing. Tests based on normal distribution. To test a statistical hypothesis, we construct a test criterion based on an appropriate test statistic with a non-probability distribution. If the probability distribution of the statistic considered is not familiar, it is troublesome to perform the test procedure. Fortunately, it is known that when the sample size is large, by central limit theorem, most of the statistics are normally or at least approximately normally distributed. That is, if U is a statistic considered, then U follow normal distribution with parameters expectation of U and standard deviation of U as n become very large, or t equal to U minus expectation of U divided by standard deviation of U follow n 0 1 for large n. This important result may profitably used for the test construction. The standard deviation of any statistic is called its standard error. While testing a hypothesis h naught theta equal to theta naught, naturally taking a statistic U with expectation of U equal to theta. Using standard error of U, a test statistic t following standard normal distribution can be formed. Then for large n, the probability that it will fall in any region in its range of variation can be found using standard normal table. Testing mean of a population. Consider the hypothesis regarding the mean mu of a population. Let sigma be the standard deviation of the population. Consider the hypothesis h naught mu equal to mu naught. The alternative hypothesis may be 1 h 1 mu greater than mu naught, 2 h 1 mu less than mu naught, or 3 h 1 mu not equal to mu naught. Assume the significance level as alpha. Case 1, when sigma is known. Let x 1, x 2, etc. x n be the samples from the population with sample mean x bar and sample variance s square. In testing of the population mean mu, the sample mean x bar, which is an unbiased estimator of the population mean, is considered as the best test statistic. If h naught mu equal to mu naught is to be tested against h 1 mu greater than mu naught, we reject h naught when t equal to x bar minus mu naught into square root of n divided by sigma greater than t alpha. One can get a t alpha from the table of standard normal distribution such that p of z greater than t alpha equal to alpha, where z follows standard normal distribution. If h naught mu equal to mu naught is to be tested against h 1 mu less than mu naught, we reject h naught if t equal to x bar minus mu naught into square root of n divided by sigma less than minus t alpha. Minus t alpha is from the standard normal table such that probability of z less than minus t alpha equal to alpha. If h naught mu equal to mu naught is to be tested against h 1 mu not equal to mu naught, we reject h naught if modulus of x bar minus mu naught into square root of n divided by sigma greater than t alpha by 2. Standard normal table gives the value of t alpha by 2 such that probability of mod z greater than t alpha by 2 equal to alpha. Case 2, sigma is unknown. We have sample variance S square as a consistent estimator of sigma square. When n becomes large, expectation of S square equal to sigma square. Here we consider large sample, hence the value of S square is considered as the value of sigma square and can perform the test as already described. In case of testing with a small number of samples, we use test based on t distribution, which will be discussed later. Problem. In a sample of 49 adolescents who served as the subjects in an immunology study, one variable of interest was the diameter of skin test reaction to an antigen. The sample mean is 21 millimeter. can it be concluded from this data that the population mean is less than 30? Assume the population standard deviation is 9, significance level 0.05. Solution. Consider mu as the mean diameter of skin test reaction. Here we have to test whether the mean diameter of skin test reaction is less than 30 millimeter. That is, the hypothesis is H naught mu equal to 30 against H 1 mu less than 30. The size of the sample taken n equal to 49 and sample mean is 21 and population standard deviation sigma equal to 9. Here to test mean of a population with large samples and non-standard deviation. Then the test criterion t equal to x bar minus mu naught into square root of n divided by sigma. So, here t equal to 21 minus 30 into square root of 49 divided by 9, that is equal to minus 7. Given significance level is 0.05 percentage. Hence, from standard normal table t alpha equal to 1.65. Here the calculated value of t equal to minus 7 less than table value 1.65. Hence, we reject the hypothesis H naught. Then it can concluded from data that the population mean is less than 30. Note. Here the rejection or acceptance of the null hypothesis was based on the comparison of the calculated value of the test statistic with the table value. This approach is critical value approach. Apart from this, a p-value approach also exists. In p-value approach, for alternative hypothesis of the type H 1 mu greater than mu naught, that is, for a right tail test, we find the probability that the test statistic to be greater than its calculated value under the condition that null hypothesis is true. This probability is called p-value denoted by p. When the test statistic considered follows n01, the p-value is shaded in the following figure. For alternative hypothesis of the type H 1 mu less than mu naught, that is for a left tail test, we find the probability that the test statistic to be less than its calculated value under the condition that null hypothesis is true. This probability is denoted by p. For alternative hypothesis of the type H 1 mu not equal to mu naught, that is for two tailed test, we find the probability that the modulus value of the test statistic greater than its calculated value under the condition that null hypothesis is true. This probability is denoted by p. In p-value approach, we reject null hypothesis if the p-value is less than the significance level permitted, or in other words, we can say p-value is the smallest significance level at which the null hypothesis can be rejected. If we are adopting p-value approach in the above problem, for the calculated value of t which is minus 7, from the standard normal table probability of t less than minus 7 is approximately 0. Since the p-value less than the given significance level 0.05, we reject H naught. Problem. A survey of 300 similar sized hospitals revealed a mean daily census in the pediatrics service of 27 with a standard deviation 6.5. Do these data provide sufficient evidence to indicate that the population mean is greater than 25, significance level 0.05? Solution. Let mu be the mean daily census in the pediatric service. The sample size is 300 with the sample mean 27 and sample standard deviation 6.5. It is to test whether the population mean daily census in the pediatric service greater than 25. That is to test whether the data agrees with the hypothesis that the population mean is 25. That is to test H naught mu equal to 25 against H 1 mu greater than 25. The population standard deviation is unknown, but since it is a large sample, approximate population standard deviation with sample standard deviation. Then the test criterion is t equal to x bar minus mu naught into square root of n divided by s, that is 27 minus 25 into square root of 300 divided by 6.5, that is 5.329. Given alpha equal to 0.05, from standard normal table T alpha equal to 1.65. Here the calculated value of T equal to 5.329, which is greater than the table value 1.65. Hence, reject H naught. That is, the data agrees with the hypothesis that the population mean greater than 25. Testing the inequalities of means of two populations. Let mu 1, mu 2 be the means and sigma 1, sigma 2 be the standard deviations of two populations, and let to test H naught mu 1 equal to mu 2. If H 1 mu 1 greater than mu 2, reject H naught if t equal to x bar 1 minus x bar 2 divided by square root of sigma 1 square by n 1 plus sigma 2 square by n 2 greater than t alpha, where t alpha is from the table of standard normal distribution, such that probability of z greater than t alpha equal to alpha, where z follows standard normal distribution. If H 1 mu 1 less than mu 2, reject H naught if t equal to x bar 1 minus x bar 2 divided by square root of sigma 1 square by n 1 plus sigma 2 square by n 2 less than minus t alpha. If H 1 mu 1 not equal to mu 2, reject H naught if t equal to modulus of x bar 1 minus x bar 2 divided by square root of sigma 1 square by n 1 plus sigma 2 square by n 2 greater than t alpha by 2. Standard normal table gives the value of t alpha by 2 such that probability of modulus of z greater than t alpha by 2 equal to alpha. Remark: if sigma 1, sigma 2 are unknown, since the sample size is large, the values of sample standard deviations S1, S2 are approximated to perform the testing. If sigma 1, sigma 2 are unknown, and in addition it is assumed that sigma equal to sigma 1 equal to sigma 2, then the value of sigma is approximated by square root of n 1 s 1 square plus n 2 s 2 square divided by n 1 plus n 2. Problem: a sample of 400 men from South India has mean height of 170 centimeters and a standard deviation of 30 centimeters, while a sample of 200 men from North India has a mean height of 178 centimeters with a standard deviation of 32 centimeters. Do the data indicate that North Indians are on average taller than the South Indians? Solution: large sample of sizes 400 and 200 respectively are taken from the two populations, and their mean is found to be 170 and 178. The sample standard deviations are 30 and 32 respectively. Let mu 1 be the mean height of South Indians and mu 2 be that of North Indians. To test H naught, mu 1 equal to mu 2 against H 1 mu 1 less than mu 2, the test statistic used is t equal to x bar 1 minus x bar 2 divided by square root of sigma 1 square by n 1 plus sigma 2 square by n 2. Since the sample size are large, then if sigma 1 square and sigma 2 square are unknown, they are approximated by the sample variances. Hence, here t equal to 170 minus 178 divided by square root of 30 square by 400 plus 32 square by 200, that is equal to minus 2.94. Reject H naught if t less than minus t alpha. Consider a significance level of 5% from the standard normal table t alpha equal to 1.65. Therefore, here t equal to minus 2.94 less than minus t alpha, that is equal to minus 1.65. Hence, reject H naught. That is, the data indicates that North Indians are on the average taller than South Indians. Note: by p value approach from standard normal table, the p value probability of t less than minus 2.94 equal to 0.0016. Since p value less than the significance level 0.05, reject H naught. Test based on chi-square distribution. 1. Goodness of fit. The chi-square test of goodness of fit is one of the simplest and most commonly used non-parametric tests of significance by Carl Pearson. It is the most suitable test to compare the obtained set of observed frequencies in a given set with a set of theoretical frequencies within them. Consider a set of n possible events arranged in classes or cells. Let these events occur with frequencies O1, O2, etc. On, called observed frequencies. Out of n observations, the expected or theoretical frequency of each possible event can be evaluated from the knowledge of the probability distribution suggested for the population. Let they are denoted by E1, E2, etc. En. Our problem is to verify whether the suggestion regarding the probability distribution of the population is acceptable. That is to test the compatibility or discrepancy of observed and theoretical frequencies, or to determine whether the deviations, if any, of the observed frequencies from the theoretical frequencies are small enough to be regarded as due to fluctuations of random sampling, or whether they indicated that the data could not have possibly come from a population giving rise to theoretical frequencies. A measure of discrepancy existing between the observed and expected frequencies can be found by using the test statistic chi square, and is given by chi square equal to summation over I from 1 to n OI minus EI the whole square divided by EI, which follows chi square distribution with n minus 1 degrees of freedom. Consider significance level alpha, then find chi square alpha from the table of chi square distribution for n minus 1 df, such that probability of chi square n minus 1 greater than chi square alpha equal to alpha. If the calculated value of chi square greater than chi square alpha, it is to conclude that the data could not have possibly come from a population giving rise to theoretical frequencies. That is, our hypothesis regarding the probability distribution of the population is rejected. In other words, the assumed probability distribution is not fitting in good to the population considered, or the fit is not good. Conditions for validity of chi square test. 1. The sample size n should be large, say greater than 50. 2. The theoretical frequencies of each class should be at least 5. If that of any class is less than 5, that class should be combined with the adjacent class and the corresponding frequencies are added together. This process or pooling should be repeated till the frequency in all classes are greater than 5. 3. The degree of freedom of chi square is 1 less than the total number of classes. If R parameters are estimated using the observations for the calculation of the theoretical frequencies, then the degrees of freedom of chi square is n minus R minus 1, n is the total number of classes after pooling. Test based on T distribution. 1. To test mean of a normal population when sigma is unknown. Consider a normal population n mu sigma. To test h naught mu equal to mu naught. If the population standard deviation is unknown, and since the sample size is small, the test based on normal distribution is not applicable. Under the assumptions, 1. The population from the sample are taken is normal. 2. Standard deviation of the population is unknown. 3. The sample size is small, say less than 30. The statistic t equal to x bar minus mu naught into square root of n minus 1 divided by s, which follows t distribution with n minus 1 degrees of freedom, is considered as the test statistic. Let alpha is the significance level, then if h 1 mu 1 greater than mu naught, reject h naught. If t greater than t alpha, where t alpha is from table of t distribution for n minus 1 df, such that p of t n minus 1 greater than t alpha equal to alpha. If h 1 mu 1 less than mu naught, reject h naught if t less than minus t alpha, where t alpha is from table of t distribution for n minus 1 df such that p of t n minus 1 less than minus t alpha equal to alpha. If h 1 mu naught equal to mu naught, reject h naught if mod t greater than t alpha by 2, where t alpha is from table of t distribution for n minus 1 df such that p of mod t n minus 1 greater than t alpha by 2 equal to alpha. Problem. A random sample of 10 boys had the following IQs 70, 120, 110, 101, 88, 83, 95, 98, 107 and 100. Do these data support the assumption of a population mean IQ of 100? Solution. From the given random sample of size 10, we find the sample mean and sample standard deviation. To perform the t test for testing h naught mu equal to 100 against h 1 mu not equal to 100, sigma over I x I equal to 972. This implies x bar equal to 1 by n summation over I x I, that is 972 divided by 10, that is 97.2. X values 70, 120, 110, 101, 88, 83, 95, 98, 107 and 100. The corresponding x I minus x bar values minus 27.2, 22.8, 12.8, 3.8, minus 9.2, minus 14.2, minus 2.2, 0.8, 9.8 and 2.8. The corresponding x I minus x bar all square values 739.8, 519.8, 163.8, 14.4, 84.6, 201.6, 4.8, 0.6, 96 and 7.8. S square equal to 1 by n summation over I x I minus x bar all square, that is equal to 1833.2 divided by 10, that is 183.32. This implies S equal to 13.54. The test statistic is t equal to x bar minus mu naught into square root of n minus 1 divided by S, that is equal to 97.2 minus 100 into square root of 9 divided by 13.54, that is equal to minus 0.62. Consider 5% level of significance. Then the value of t alpha by 2 from table of t distribution for 9 degrees of freedom is 2.262. Here modulus of t equal to 0.62, which is less than t alpha by 2. Then we accept h naught. That is, the data support the assumption that the mean IQ is 100. Test based on statistics following F distribution. To test the equality of standard deviations of two normal populations. To test h naught sigma 1 equal to sigma 2 against h 1 sigma 1 not equal to sigma 2, where sigma 1 and sigma 2 are the standard deviations of two normal populations. Let S 1 and S 2 be the standard deviations of the sample of sizes n 1 and n 2 is taken from the two populations. The test statistics suggested is the ratio of the unbiased estimators of population variances, that is, if n 1 S 1 square by n 1 minus 1 greater than n 2 S 2 square by n 2 minus 1, F equal to n 1 S 1 square by n 1 minus 1 divided by n 2 S 2 square divided by n 2 minus 1, that is n 1 into n 2 minus 1 into S 1 square divided by n 2 into n 1 minus 1 into S 2 square. F follows F distribution with n 1 minus 1 comma n 2 minus 1 degrees of freedom. For a significance level alpha, reject h naught if f greater than f alpha by 2, where f alpha by 2 is from the table of F distribution for n 1 minus 1 comma n 2 minus 1 degrees of freedom, such that probability of f n 1 minus 1 n 2 minus 1 greater than f alpha by 2 equal to alpha by 2. If n 2 S 2 square by n 2 minus 1 less than n 1 S 1 square by n 1 minus 1, then consider f equal to n 2 S 2 square by n 2 minus 1 by n 1 S 1 square by n 1 minus 1, that is n 2 into n 1 minus 1 into S 2 square divided by n 1 into n 2 minus 1 into S 1 square, which follows F distribution with n 2 minus 1 comma n 1 minus 1 degrees of freedom. Reject h naught against H1 sigma 1 not equal to sigma 2 if f greater than f alpha by 2, where f alpha by 2 is from the table of f distribution for n 2 minus 1 n 1 minus 1 degrees of freedom, such that p of f n 2 minus 1 n 1 minus 1 greater than f alpha by 2 equal to alpha by 2. If H1 sigma 1 greater than sigma 2, reject H naught if f greater than f alpha, where p of f greater than f alpha equal to alpha, and if H1 sigma 1 less than sigma 2, reject H naught if f less than f alpha dash, where p of f less than f alpha dash equal to alpha. Problem. Rats were grown under two experimental conditions. Two random samples of 11 and 9 rats show the sample standard deviations of their weights as 0.8 and 0.5 respectively. Assuming the weight distributions is normal, test the hypothesis that the true variances are equal at 10% level of significance. Solution. Let the population variances of the populations from which the sample of sizes 11 and 9 are taken respectively sigma 1 square and sigma 2 square. To test H naught, sigma 1 equal to sigma 2 against H 1 sigma 1 not equal to sigma 2. The sample variances S 1 square and S 2 square are 0.8 and 0.5 respectively. Here n 1 S 1 square by n 1 minus 1, that is 11 into 0.8 square by 11 minus 1 equal to 0.704, and n 2 S 2 square by n 2 minus 1 equal to 9 into 0.5 square by 9 minus 1, that is 0.28125. This implies n 1 S 1 square by n 1 minus 1 greater than n 2 S 2 square by n 2 minus 1. Hence, the test statistic is f equal to n 1 S 1 square by n 1 minus 1 divided by n 2 S 2 square by n 2 minus 1, that is n 1 into n 2 minus 1 into S 1 square divided by n 2 into n 1 minus 1 into S 2 square, that is 11 into 9 minus 1 into 0.8 square by 9 into 11 minus 1 into 0.5 square, that is 2.503. At 10% significance level from f table of 10,8 degrees of freedom, f alpha by 2 equal to 3.35. In this case, f less than f alpha by 2, hence no reason to reject H naught. That is, the equality of the population variances may be accepted. Analysis of variance, ANOVA. Analysis of variance, ANOVA provides a statistical test of whether or not the means of several groups are all equal, and therefore generalizes t-test to more than two groups. Doing multiple two sample t-tests would result in an increased chance of committing a type 1 error. For this reason, ANOVAs are useful in comparing 2, 3 or more means. Assumptions in ANOVA. The populations from which the samples were obtained must be normally or approximately normally distributed. The samples must be independent. The variances of the populations must be equal. One-way ANOVA. Let the data are classified according to only one characteristic. Consider independent sample of n1, n2, etc. nk observations from different populations with population means mu1, mu2, etc. mu k. Then one-way ANOVA is to test the arithmetic means of the population from which the k samples are randomly drawn are equal to one another, or it is to test the hypothesis H naught mu1 equal to mu2 equal to etc. equal to mu k. Procedure for one-way ANOVA. Let us consider we have k independent samples. Assume samples containing respectively n1, n2, etc. nk items. The total number of items in the sample is n1 plus n2, etc. plus nk, that is equal to n. The steps for ANOVA for testing H naught mu1 equal to mu2 equal to etc. equal to mu k are listed as follows. Step 1. Obtain the sample means of each of the k samples. Let it be x bar 1, x bar 2, etc. x bar k. Step 2. The grand average of the entire n sample items, x bar is found as x bar equal to x bar 1 plus x bar 2 plus etc. plus x bar k all divided by k, where k is the total number of samples. Step 3. Take the difference between the means of the various samples and the grand average. Step 4. Find the sum of squares of these differences multiplied by the number of elements of each group. This number is the sum of squares between the samples SSB. Step 5. Mean sum of squares between the samples is MSB, that is equal to SSB divided by K minus 1. Step 6. Take the deviations of the various items in a sample from the mean of the respective sample and add the squares of such deviations. This number is the sum of squares within the samples SSW. Step 7. Mean sum of squares within the samples is MSW equal to SSW divided by n minus k. Step 8. Calculate F ratio, where the ratio F equal to MSB divided by MSW. Step 9. Compare the calculated F with the table value of F distribution with the degrees of freedom k minus 1, n minus k. Step 10. If calculated value of F is less than the table value, accept the hypothesis that the population means are equal. Problem. Among 3 groups of 5 rats, each group are given different varieties of foods. Their gain in weight are measured and given as follows. Test the significance of the differences between the nutrition as far as the gain in weight is considered. Group 1, 12, 10, 14, 11 and 13. Group 2, 8, 9, 13, 10 and 10. Group 3, 7, 6, 16, 11 and 15. Solution. To test the mean gain in weight due to the 3 foods are same. Mean sample weight of each group are x bar 1 equal to 1 by 5 into 12 plus 10 plus etcetera plus 13, that is equal to 12. X bar 2 equal to 1 by 5 into 8 plus 9 plus etcetera plus 10, that is 10, and x bar 3 equal to 1 by 5 into 7 plus 6 plus etcetera plus 15, that is equal to 11. Hence, the grand average x bar equal to x bar 1 plus x bar 2 plus x bar 3 divided by 3, that is 12 plus 10 plus 11 divided by 3, that is equal to 11. SSB equal to 5 into 12 minus 11 square plus 10 minus 11 square plus 10 minus 10 square, that is equal to 10. MSB equal to SSB by k minus 1, that is 10 by 3 minus 1, that is equal to 5. SSW equal to 12 minus 12 square plus 10 minus 12 square plus etcetera plus 8 minus 10 square plus 9 minus 10 square plus etcetera plus 7 minus 11 square plus 6 minus 11 square plus etcetera plus 15 minus 11 square, that is equal to 106. MSW equal to SSW divided by n minus k, that is 106 divided by 15 minus 3, that is 106 divided by 12, that is equal to 8.833. F equal to MSB divided by MSW, that is equal to 5 divided by 8.833, that is 0.566. F table value for 212 DF at 5% significance level is 3.88. Since calculated F is less than the table F value, we accept the hypothesis that all the foods are having same impact. Now, let us summarize. Some important statistical tests are discussed in this module. This includes the test based on normal distribution, chi-square distribution, t distribution and F distribution. Theoretical parts of the tests are mentioned and the testing procedure is illustrated through some problems. ANOVA is also considered at the end of the module. Please try to answer the following questions. 1. Diastolic blood pressure for the population of female diabetics between the ages of 30 and 34 is normal with unknown mean and standard deviation 9.1 millimeter of mercury. From a sample of 10 women, the mean diastolic blood pressure for the population of female diabetics is 90 millimeter of mercury at 5% level of significance. A sample of 550 people from rural population of a developing country gives the mean daily caloric intake as 1980 with a standard deviation 220. Do the data support the hypothesis that the mean daily caloric intake of the population is less than 2000 at 5% level of significance? Next question. The following are the systolic blood pressure in millimeter of mercury of 10 patients undergoing drug therapy of hypertension: 176, 182, 175, 154, 168, 145, 179, 135, 188 and 139. Can we conclude that the mean systolic blood pressure of the population is less than 150 at 5% level of significance? The daily fat intake of 180 randomly selected men from city A is 56 grams with standard deviation 29 grams, and that of 210 men selected from city A is 59 grams with standard deviation 27 grams. Test whether the data contradict the null hypothesis that the two cities are having the same mean daily fat intake at 5% level of significance. Books for your reference are: 1. Marcelo Pagano and Kimberly Guerrio, Principles of Biostatistics, Signage Learning. 2. Methi J, Statistical Methods and Introductory Text, New Age International Private Limited. 3. Bud B.R., Sri Venkatramana T and Madhav Rao K.S., Statistics, a Beginner's Test, New Age International Private Limited. 4. Gupta S.C. and V.K. Kapoor, Fundamentals of Mathematical Statistics, Sultan Chand and Sons. 5. Daniel W. Biostatistics, John Wiley Sons. Hope you enjoyed this session. See you next time. Until then, goodbye.